Hi guys, Big Monday here, and today I have a Starmade logic tutorial for you. We're going to start off just doing a recap on binary counters, because the previous guide I made on them, they weren't as efficient as they could have been. I sort of laid it out a bit more elongated than necessary to sort of break down each step. Now I've basically made the same thing but all condensed. So, binary. If you don't understand binary, go and take a look on Wikipedia, on Google, how does binary work. But basically the gist of it is, you can store numbers in ones and zeros. Or in this case we're using flip-flops to store numbers in off and on. On is 1, off is 0. Currently, if they're all off, that represents 0, and then we can just we can count each step to work out what we're on. So if we don't know, we wait until they're all orange and then we count each step. Bear in mind, all orange is 0, so once we get to all orange, that's 0, and then we'll go 1, 2, 3, 4, 5, 6, 7, 8, and so on. This one goes up to, them all being blue represents 15 on this. So this binary counter is 0 to 15. It's important we recognise with computers that it is 0 and not 1. Computers count from 0, not from 1. Now I'm counting this round with a pulsar, which is basically a timer fed into a NOT gate, which is fed back into the timer, and that will just do a half-second pulse again and again and again. It takes 2 pulses to make this progress 1 step. So basically every second it will count up 1. Now we could extend the timer if we wanted with more timer blocks to make a 2-second count or a 3-second count or a 5-second count, but that's usually not necessary. And the whole point of these and why they're so useful is we can make really long clocks and really long timers without a ridiculous amount of stuff. So, how does this work? Basically, to build one, you're going to need a flip-flop for each bit. The more bits you have, the more numbers it will count up to, and basically every time you add a bit you have twice the number of combinations. So bear that in mind. If I were to add a 5th on here, instead of having 16 options I would have 32, add another and it's 64, and that might give you a clue to how these can be useful as clocks, because we add 3 new blocks and we've got twice the length, and then we add 3 new blocks again and twice the length, and you can't do that with timers. You just have to add the same number of timers to double it. So at the back we have the first block that we feed into, and basically we feed the pulse into that one. That will be linked to every AND gate at the back here, and it will be linked to the NOT gate directly in front of it. So then we have a row of NOT gates here, and each one of these AND gates at the back is also linked directly to the NOT gate in front of it, and nothing else. Then we have a flip-flop. Each flip-flop, each NOT gate in the middle row then links into these flip-flops, and each one links directly into the flip-flop in front of it. So then we can start to get a bit more complicated, where we go across columns. We'll start with this one. It's the one on the far right. If you saw my previous logic tutorial, my binary counter went from left to right. This one goes from right to left, or at least the way I'm looking at it in this. So it's kind of a mirror image, in case that's confusing you. So we look at the flip-flop, and it connects to every AND gate that is in a left column. So we take the next flip-flop, you see how we miss the column it's in, and then every AND gate to the left. So if you want to continue that on to have like 500 flip-flops, You just have to miss the column it's in and then connect every AND gate that's to the left. And that's basically it. And this will then count up. It will count up to whatever number. In this case, it goes 0 to 15. Now you can just continue this to the left and just keep going left and left and left and left and left. But that starts to take up a lot of space. So with this one, what I've done is we basically just slap the 4 that would have been to the left, we put them on top. So the wiring gets a little bit awkward because when you're connecting the flip-flops and we go every AND gate to the left, you then also include every AND gate that's on a higher layer. So as you go up the layers, it includes all of those on the higher layer. But otherwise, it works exactly the same. All the AND gates at the back feed directly into the NOT gate in front of them. All the NOT gates feed directly into the flip-flop in front of them. Now this one, this is an 8-bit. It's got 8 flip-flops, that is 8-bit. And this gives us 0 to 255. So this has 256 different positions. So it's only got 4 more rows. So that's quite a big jump from the 16 positions. But every row it doubles it. So it goes 16 to 30 to 32 to 64 to 128, 256. And then we can do the same thing again. We can put another layer on, just to, why not have massive size? Everybody loves massive. And this is exactly the same again. The AND gates will feed into all the NOTs in front of them. The NOTs will feed into the flip-flops in front of them. Every flip-flop feeds into every AND gate in a layer above it, and every AND gate in the same layer to the left. Okay, and they're both the same. We have a NOT gate as the triggering gate down here. Really simple. And you see this one, it goes from 0 to 4095. That doesn't sound right. I may have... Yeah, so there's 4096 combinations in this. Right, so how do we make this useful? I mean, the whole point of this, we don't just want a really long timer. And if you do just want a really long timer, this can work. It works as a really long timer. As you can see, it's slowly counting up, filling up the whole set of flip-flops with blue, ever so slowly. Eventually, once it gets full, it will reset. So it could just be a really long timer if we wanted. We could set an AND gate that is AND on all of these. So only when it reaches its maximum value it will do something, and that could give us that massive, massive timer. But that's not that useful. It can be a little bit useful, but what makes these really, really useful is the versatility in the fact that you can tie an action into each individual step. So if we go back to this one, this has 255 positions. What I've set up here is we are pulling out a number from those certain positions. And those numbers, I've put them on here. So it goes 16, 194, it does 0, and it does 255. So in order to get a number, we are going to need another NOT gate for every flip-flop. Now, to condense this, you could put the NOT gate directly in front of the flip-flop. So we'll put a flip-flop and it connects directly to the NOT gate in front of it. So, because we need to be able to take the signal of something the flip-flop is on and the flip-flop is off, and we need to be able to feed that signal into something. So we put the flip-flops in as well, put the NOT gates in as well in front, and basically this would then make us a nice little 4x4 grid. So then after that, we will set the binary counter on a number, whichever number we want. You're going to have to sit and work out which flip-flops need to be on for which number. you know, do some binary math. If you don't know your binary well and you can't work it out, there are apps on most phones. On Android, there is an app that will convert binary to decimal and hex and pretty much everything. So go download one of those apps, it'll help you. So basically you then wait until the flip-flops are on the correct number. Just let me turn this off. So I'm going to whip out my binary converter. If I have it installed, I hope I do. Wasn't actually planning on going into this much detail. I have a program called Hex Plus. Now, every blue block represents a 1 and every orange block in the flip-flops represents a 0. So in binary, we now have 1 1 0 0 0 1 0 1. Just double check that. 1 1 0 0 0 1 0 1, which converts to 197 in decimal. Okay, so to pull that number, we then need two AND gates. And we'll go AND gate, AND gate. Now the back AND gate connects to the front one. And then we work out, now we're currently on 197. So the back AND gate, we find all the blue knots and connect them to the back AND gate. It's probably a little bit difficult to see with all these pipes, I'll just get in close. So basically got all the blue NOT gates and connected them to the back AND gate. And then we take all the blue flip-flops and connect them to the front AND gate. Now when you connect it, it won't do anything the first time. But once it ticks around again, it will light up. So just to sort of cheat a bit, let's turn that off. Okay, so we're now on 1 1 0 0 0 1. I may have accidentally incremented it. I've gone up. Okay, we need to go down. Okay, we are currently on, doing my binary calculations, 1 1 0 0 0 0 1 0. That's 194. So let's start the binary clock again. Let's get in the build block because it gives me a bit more range. Okay. And there we go, it lights up 3 steps later. So this will continue to go around. You just have to bear in mind when you first link things up, it won't update all the logic circuits you put down when you do the linking. Okay, so next step. Once we can pull an actual number from it, we can use the block on that number to feed into logic circuits at different points in the step. For example, you could have a rail that starts moving on position 1, stops moving on position 30. You then have a rotating platform that moves from 30 to 60, and so on and so forth. So this can kind of get complicated. Part of the way I've used this in the past with just a 16 position is you link the 16 positions into different sets of lights. So you can have like pulsating lights and a disco that go in, and each set of lights will go in a different combination. So, you know, have a play around with it. The point is you can pick and choose numbers in different positions to either have longer delays between different steps and do things in certain order. See, normally when you just have timer blocks, every step is the same length, whereas this, it lets you stagger things out in different lengths. Okay, so the next step is a computer core. So what's the difference between a counterclock and a computer core? Well, a computer core has an output ready-made for every number in its sequence. So I've got this one over here, and on its base level it's just one of these. It's a 0 to 15. And the 0 to 15 so basically we put an output for each one of those 0 to 15, and you can see this on top. It counts across all the numbers. Bear in mind it starts from 0. So if I look down on it, it's going to get to 15, and it goes 0, 1, 2, 3, roughly a second apart. Now, the way we're able to conveniently condense this into a nice little cube is because the output for 0 means that the output for 0 is, it only needs to know the state of one type of gate. It doesn't need to know the flip-flops and the NOT gates. And notice how previously to get numbers we needed a NOT gate. Now these are kind of hidden in the, you can see the flip-flops in this side. They're actually, the NOT gates are on the opposite side of the cube. Now the reason for that is because when we start to wire up bigger computers, getting access to the flip-flops and the NOT gates when they're in the way of each other. Because if I put them on the front, like here, you wouldn't be able to get to them. Now in a one-layer computer you could sort of dig away the floor and go underneath. But imagine in a two-layer computer like this. I mean, if I put the NOT gates here, how do you get to the flip-flops? You can't. You just can't get to them. So we put them on the opposite side, and if you watch carefully, watch that one. It's always in the opposite state to that one. So basically, this NOT gate, so this flip-flop is connected to this NOT gate, and this flip-flop is connected to this NOT gate, and so on and so forth. So position 0 and position 15 differ from all the other positions in that they only need to know the state of the flip-flops or the NOT gates. They don't need to know both, because the NOT gates will be all the same. Now let me just stop the pulsar here. I'm going to put a button. Button, who's got the button? I'm going to put the button so I can manually trigger it and feed it into my initial. Is that still? Did I put a pulsar on this? Oh, I did. I put its own pulsar on. Let's deactivate that. Okay, so we feed our pulse into this NOT gate at the back. That NOT gate is the same as that NOT gate. But what I'm going to do, I'm going to feed it with a button just so I can manually control it, and so I can step it one at a time. And I'm going to step it round to 0. Okay, we're on 0. So as you can see, no flip-flops are lit up, and all the NOT gates are lit up. So all we have to do for the 0 position is we feed all of those NOT gates into one AND block. And so we only need the one AND block, and because we can save that one space, we can take that one out and that one out. Now if I fast forward to position 16, okay, position 16, all the flip-flops are lit up, so I can get away with just using one AND gate. So I don't need an AND gate for the NOT gates and an AND gate for the flip-flops. You only need one for the highest number and the lowest number. And that gives us space in this cube to put the pulsar within the cube so that both the computer and the pulsar that drives its clock, they all fit within this neat little cube. So all the other numbers will work in exactly the same way we set the number up before. We find whatever number we want. Let's take 3, and then we feed all the blue NOT gates into the back AND gate, the rear one, which in this case is going to be from a top-down view. So we feed all the blue NOT gates into the back AND gate. We feed the back AND gate into the front, and then we feed all the lit up flip-flops into the front AND gate, and that represents R3. So again, if you are only going to use this in one instance, it doesn't really give us any advantage over manually wiring up the numbers we want. But once you have built this, and once you have got this computer, we can use the copy and paste function. So we can load, and I want a 0 to 15 computer core, and the computer core, we will go paste, and I'll put a computer there, and a computer there, and a computer there, and I already have all 16 outputs on the top. So I can link up whichever ones I want. Now I might not need half those outputs. I might not need 3/4 of those outputs. So it kind of feels like I'm wasting space with this circuit, but the point of this computer core is to make like a standard output, rather than having one that's tailored to the task. We have this multi-purpose processor that can give us any number in the sequence, rather than just the few numbers. So I'm going to just undo that. Now what we can do, we can actually drive more than one circuit from the same set of numbers, from the same computer core. So we could have this, we could have it drive a set of lights, we could have it drive numbers on a clock face, we could have it drive different motions, and it can drive more than one circuit from the same computer core. So as long as you only need 16 steps, it's fine. I mean, each of these AND gates that gives us an output, let me just get rid of that. Each of these AND gates that gives us an output can feed into multiple different logic circuits. So we can feed into as many things as we like from the computer core. Now we're starting to get a little bit more complicated. So I'm going to paste my next computer in. Now this is a 64, I think. No, this is a 32 position computer core. And the reason I'm going to paste it is because I'm going to take some of it apart, because part of what I've put in here is just for cosmetics. Now if I start this running, again, just like with the other one, it's got the pulsar built in. So this row, if I were to go all the way back through this row, that entire row is the pulsar for this computer core. But it has this block on this activator block on the front, which is to turn it on or off. It's not 100% reliable. You have to sort of flip the state a couple of times to get it to start. Okay, so as we can see, we have 5 flip-flops. So we have 2 positions, 4, 8, 16, 32. So these don't have to be in even numbers wide. You can have 3 on the bottom row and 7 on the top row. You can have any order you like, as long as you wire them up. As I said before, you go from left to right, and then you go to the next row up and go to left to right. Next row up, left to right. As long as they're in that sort of logical order. So we have 32 positions on this. Now, those 32 positions on the left-hand side here, on the left-hand side here, it goes from 0 to 15. So on this is bank 1, goes from 0 to 15. And on this side, it goes from 16 to 31. There we go, 16 to 31. Now, the lights in the middle here, all these rows in the middle are cosmetic, because the whole point of a computer core is to have some sort of a logical arrangement to make things easy to wire up to the certain numbered outputs. And to do that, we ended up with one set of outputs here and one set of outputs on the other side. Now, we probably could have condensed it down and maybe had it one less wide by using all this space in the middle, but it wouldn't have had a logical arrangement, which would have made it really awkward to wire up. So, just to make things simpler, I'm going to take out these blocks. All they are is there's a set of OR blocks in the middle, and each of those OR blocks is connected to sort of different random outputs, and each OR block then connects to a light, just to make the lights blink in a really random order. But all this sort of middle bit is just cosmetic. So we can take that out, 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 we can take that out. Here is our pulsar, we can take that out, and as you can see, we are left with 5 rows of our binary counter in the middle, with the NOT gates on the opposite side, just like we had with this one. So, can we go further? Is the next question. Logically, yes, we can go further, because as you can see, it's not practical to have more than a 4x4 block on either horizontal side. So that leaves us, we've got 32 here, we could have a horizontal block here, and we could have a horizontal block here. So we could have this 4x4 on the front and the back as well. To make that fit, we would extend these to 4 wide, just so that we've got room to get another set of these 4 wide. And we can only go then 2 rows deep. And the reason we can only go 2 rows deep is because we need, to be able to wire it up, we need access to all of these NOT gates. So if we had a big wall of our outputs here, and we try and go 3 rows deep, we're just not going to be able to get to them. It's not practical. If you need more output after that, you have to put more than one computer in. So you put a dual core computer. So you would place this computer, and then instead of having a pulsar drive this computer, you would have the last output drive the next computer, if that makes sense. So once this reaches its 32nd position, you have that output drive the next core. So you probably noticed there's pipes everywhere, absolutely everywhere, and this gets a little bit messy. Now we can solve that by going into creative mode. Well, you won't need to go into creative mode to do this, but you will possibly have noticed, if you've set up wireless before, that if you try and connect a wired trigger, so a wireless trigger to a wireless activation module, on the same entity, so on the same ship or the same station, you still get a pipe. And that looks hideous. And what we want to be able to do is we want to turn around to this computer and say, right, I want number 1, I want number 8, and I want number 12. and you then go wherever you have your logic that you need those 3 outputs for, and you go 1, 8, 12. And you should be able to link them like that without getting it ugly. Because I'm using wireless, and look, it's wireless, it should work. But I still get the pipes, and they still spoil the look of my base. So how do we get around that? First, we delete this computer because it is now in the way. Remove. We go 1, 2, 3. Okay, we need a computer core and a docking module. Sorry, a ship core and a rail docker. Rail docker, rail docker. Hello. Where are we? Where are we? It stacks, if I remember rightly, in creative mode. It could just be using the search function. Okay, rail docker. And I'm also going to need a rail. So, the rail, I'm going to put a rail on here. Just take move mode off. Get the rail the right way up. I'm going to come out of build mode. And wander over to where I put that rail. And I'm going to place a new ship. Central computer core, even though it was spelt wrong. I'm going to get in my ship core. And I'm going to place, let's get some grey hull on it. And what we're going to do is we're going to place grey hull in such an arrangement that it looks like this ends up looking like it's part of our station. In fact, I'm not using grey hull, I'm using white. So let's use white. So I'm going to go 1, 2, 3. Let's get the mirror axis on just to save me a bit of time. Build ourselves a little platform. Okay, so now we're going to take out a single block in the center. Get our rail docker facing the right way. Awesome. Probably didn't need that one at the back. Let's take that out. It's unnecessary. We don't like things that are unnecessary. And now we're going to paste our computer in. I'm going to rotate it to a more logical direction. Make sure it's the right way up too. Page up and page down, by the way, to rotate like that. I'm going to place it there. So now we have a computer core sitting on what is effectively a ship. If I go into paste mode now, with my we go back to the wireless logic modules, and I'm not going to wire all of these up because it takes forever. We press C to select one of our outputs and put a wireless in. C and a wireless. Notice it doesn't update the one that was already on. C and a wireless, 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 C and a wireless. Okay, so we do that for all of the outputs, all of them. And now we go into fly mode, and we have no thrust, so this is going to take forever. We need to put the rail docker on our on our. Okay, and let's select the rail docker before we fly too far, and there we are. We are docked. Come out of the ship, and we notice it. If we put the white armor in just the right place, it actually looks like it's one ship. You could, if you wanted to, be really clever and put this on some sort of rotating gyroscope system with multiple turret rotators, rail rotators, sorry, multiple rail rotators to get this, and you could have it rotate on different steps of your computer core, which would look really cool. But okay, so now this is actually a ship. If we place down a wireless logic module, and we want, okay, so that's 16, 17, 18, 19, 20, 21, 22, 23, so that's 23, 24, 25. Okay, so 23, and we connect it. It is now connected. Connect it. It is now connected. And now we'll start her up. And again, we have to pump the output once to get everything to fire up. And there we go. And those wireless modules will now fire. We could put all 32 outputs from the computer, and we can place them anywhere in our base we liked, and we won't get pipes everywhere. So we now have the flexibility of having all 32 outputs in any configuration we like, and also the flexibility of not having pipes everywhere. So we can take this all the way across our base. So basically we have one central computer core, and for everything that requires up to 32 steps, we don't need to build more logic circuits to order it. All we have to do is build these wireless modules and go connect them to the right number. And happy days. Happy days. All is well with the world. Okay, so guys, hope you found this useful. I appreciate it's gone a little bit long, and if you are not mad on logic, this stuff drags out a bit. But you can make some really cool shit with this. Like, you can make folding doors with you can basically make hangar doors that have an operating sequence to them. Rather than just be open close, we can have a door with rail rotators on that sort of folds one section of the door in, then folds the next section of the door in, then retracts the door system and stuff like that, and then it can do it all in reverse again, which is really cool. I mean, you can't argue with. You can make some really cool shit with being able to sequence stuff with this sort of level of precision and flexibility. So guys, I hope you found this useful. Appreciate I've droned on. Thank you for watching, guys. Bye bye.